In this section 3.3 of chapter 5, what we're going to be doing is drawing inferences about the variance of a population using a chi-square test. So we've seen many times before that if we know the sampling distribution, there's two kinds of inferences we can draw. We've seen null hypothesis statistical testing, and we've seen 95% confidence intervals. So we've seen those so far. And up until now, in terms of null hypothesis testing, we focused on either null hypotheses concerning an individual population mean or the difference between two population means. So what this section is going to be doing is it's going to be doing null hypothesis statistical testing, but not on these guys, rather on the population variance, again using a chi-square test. We're not going to cover 95% confidence intervals. So the way I'm going to show how we do null hypothesis statistical testing on a population variance is by example. And our example is we've got a population of trees, and we're going to assume that the underlying population is normally distributed. And our null hypothesis is that the variance of the underlying population, is equal to 20. Now, one of the things I alluded to before is that when we're using a chi-square test to draw inferences about variance, we can ignore the population mean. So even though the underlying population is normally distributed, it has this parameter mu, we can ignore it. The process that we're going to go through is going to be relevant and correct and practicable regardless of what the value of mu is. So there's a null hypothesis, there's our assumption about the underlying population. So we go out and we collect a sample of trees. We select a sample of trees size 16, and we calculate based on that sample. I'm going to do this in lowercase s to be clear. There we go. Lowercase s, and we calculate that as the sum of all the yi minus y bar all squared over n minus 1, and let's say that turns out to be 36. So on the basis of that, we can calculate our chi-square statistic, and our chi-square statistic is calculated as s squared minus n minus 1 divided by the population variance. So in this case, s squared is equal to 36. N minus 1 is 16 minus 1, or 15. And this variance, what is the variance? The variance is our null hypothesis. And we set that equal to 20. And so if we do all this algebra, the chi-square value turns out to be 27.0. So that's our observed value of chi-square. But this is just the one particular value we got. If we consider all possible values of the chi-square we could have gotten by withdrawing an infinite number of samples from our underlying population, assuming that our underlying population was normal and had a variance of 20, well, then we can think of this random variable they're going to represent as capital chi squared, and it's going to be capital S squared over n minus 1 over sigma squared. So this n minus 1, we can think of this as being 15. We can think of this as being 20. And then we've got, this is a random variable, this is a random variable. And we can think about the reason this is being a random variable. Again, if we think about all possible values of chi-square we get, well, every time we took a different sample, we get a different value of s squared. So therefore, it makes sense that this capital S squared would be a random variable. And of course, this thing value here capital chi-square represents the set of all possible values of lowercase chi-square. This is a random variable. Now what we know is, if it's a random variable, it has a probability density function. And what we're doing here is we're calculating the probability density function of chi-squared, which is a sample statistic. So the probability density function of this random variable chi-squared is a sampling distribution. And I could go online and I could find a table that would show me something that looks like this. So this would be a set of all possible values of s squared onto n minus 1 over sigma squared, where this is equal to 15 and this is equal to 20. So think about what we have here. What we have here is a set of all possible values you could have of this thing, given that that's the null hypothesis. That's what we're going to assume is the underlying population variance. All possible sample sizes of 15, and think of the infinite number of different values of lowercase s squared we could get if we repeated the experiment an infinite number of times. So this curve right here reflects the probability density function, shows on this axis we have chi-squared. This would be f of chi-squared. So probability density function of all possible values that of this statistic that might have arisen, given that this is equal to 20, given this is equal to 15. And then we look at the particular value that we got. And remember, the particular value we got when we did our experiment was chi-squared is equal to 27. So we look at this plot and we come out here and we see where 27 is. And there's 27. There's 27 right there. So there's 27. So what does this mean? What this means is if we consider all possible values of this thing here, given that the population variance is equal to 20, given that sample size minus 1 is equal to 15, if we consider all possible samples, the probability of getting a particular sample with a value of 27 is actually quite low. It's actually 0.025, which I would consider to be a rare event. And if we don't believe in rare events, then something's gone wrong. Because if this is equal to 15 and this is equal to 20, the probability of getting a 27 is really unlikely. So what went wrong? What went wrong is we're going to assume that our null hypothesis that the underlying variance was equal to 20 was wrong. So we're going to reject our null hypothesis that sigma squared was equal to 20 in favor of an alternative hypothesis that says, no, given that we observed a chi-squared value of 36, the true population variance, the variance of the underlying population, is greater than 20. So we'll stop there.